chapter 5 today and learn about nomenclature, which is a fancy word for naming compounds. And these are topics covered. We're going to start as simply as possible. And all of these rules that we're going to use have been formalized by a committee of this organization, which is the Union of Pure and Applied Chemists, International Union of Pure and Applied Chemists. Let's see, I'm not seeing what I want to see here. Hold on a second. Yeah, there I am. Okay, why don't I see me down here? Oh, well. Okay. A binary compound is composed of two elements or two groups. We're going to talk about the difference between an element and a polyatomic ion. But the polyatomic ions can substitute for a single element. But we're going to start off really simple. We're just going to say two elements combined makes a binary compound. And we're going to start off, the rules are going to be addressing ionic compounds, where you have one positive ion, one negative ion, one cation, and one anion. And that always means a metal and a non-metal. Because of the nature of elements, metals tend to lose electrons and become positively charged. Non-metals tend to gain electrons and become negatively charged when they are associated with one another. Then we're going to extend those rules to the covalent compounds, which are those that are composed of two nonmetals. If they're two nonmetals, then you can't move electrons from one to the other and create ions. So they have what we call a covalent bond, where they share electrons. What we need to know first, and I think we covered this, I believe we covered this last Tuesday. Chemical foundations, when we were talking about the periodic table. I think I made the point that there are groups, right, vertical columns in the periodic table where the elements assume a single ionic charge when they're in association with either, if they're metals, nonmetals, and nonmetals, metals. Group one, where you start off with lithium, they call it sodium, but it's group one are the alkali metals. And in association with nonmetals, they always assume a 1+ charge. There's no other option, just the 1+ charge. Whereas the halogens, fluorine, chlorine, bromine, iodine, astatine, those halogens always assume a -1 charge when they are in association with metals. Right, these are type 1. I'm gonna lay those out on the board in just a minute. We call these type 1 compounds. When the metal has only one possible charge. Type 2 compounds, well, let me just start that up here. Might as well put it on the board while we're talking about it. Type 1 compounds are metal and non-metal. Type 2s are also metal, non-metal. The difference is that in the metal here, it has a fixed charge. Okay, for the metal. And this one has a variable charge. That is, it can assume a different charge as it forms the compound. But once it's in the compound, that charge is now fixed for the compound. But it has available to it different charges. Okay. And I might as well go to type 3 while we're here. Type 3 compounds are non-metal, non-metal. Okay. These are representatives of some cations and anions. And it looks to me the anions are going to be fixed charges. I'm looking at all the cations to see. Okay. Yes, those are all fixed charges on the cation side of this table. So the first column, the alkali metals, are always +1 charge. The second column, with beryllium at the top, those are alkaline earths, and they always have a 2+ charge. Then we skip over the transition metals, and I'll come back to those in a minute. And we go to boron, aluminum, gallium, indium, that group under boron. They always have a 3+ charge. Then we move to the nonmetals. The halogens, fluorine, chlorine, bromine, iodine, astatine, those always have a -1 charge when they're in a compound with a metal. Next door to them is the chalcogens, the oxygen group. Oxygen, sulfur, selenium, tellurium, they always have a 2- charge. And the pnictogens, or the nitrogen group, nitrogen, phosphorus, arsenic, antimony, they always have a 3- charge when they're associated with a metal in an ionic compound. Carbon is kind of in between. It can go any number of ways. That's probably why living systems are made of carbon, because it's variable. Anyway, there are also some transition metals. When we have, let's see, if we have our periodic table, we have 2 columns here, and we have 6 columns here. Let's see. We have 6 columns here. Then we have the transition metals, and these last 2 over here, like that, and then these like this. Right, this one is zinc, and this one is cadmium, and this one is silver. Silver, cadmium, and zinc have fixed charges. Silver is a +1 charge. Cadmium is a 2+ charge. Zinc is a 2+ charge. Always. So those metals, these 2 columns, this group here, right? The boron, aluminum, gallium, indium group, and silver, cadmium, and zinc would fit under the type 1 compounds because they have fixed charges for their metals. All right. The rest of the metals are variable charge, like the rest of the transition metals and some that are over in this area, right? Remember that zigzag between the metals and the non-metals. Some of these, well, all of the metals on this side, except for the ones that we named here, are variable charge. So they would fit under type 2 compounds. So the nice thing about ionic compounds is since compounds are neutral, all you have to do is balance the charges. So our example here is aluminum, which in this compound has a 3+ charge. It's an ionic compound, so aluminum always has a 3+ charge. Chlorine is a halogen, so it has a 1- charge. To balance the compound and put the right number of atoms in this formula, you just have to balance the positives and the negatives. 1 aluminum gives you 3 pluses. So with chlorine only giving you 1-, you need 3 of them. So we would write the compound as AlCl3. All right. Now to name the compound, say we'll take aluminum chloride. We know that's balanced because this is a 3 plus and that's a 1 minus. But to name the compound, you name the metal first, just the element name, aluminum. And then the nonmetal gets its ending is changed to IDE. So instead of chlorine, we would say chloride. Okay, just change the ending. And that's it. I mentioned last time that the rules governing naming compounds are meant to be unambiguous, like this. This relates to that and that to that, and that's the only way it can be interpreted. There's no other way. And non-redundant. So what would redundant be for this compound? If we had to say, what is the charge on aluminum? Right? If we put something in here like this, 1, 2, 3, and say that aluminum has a 3 plus charge, because we put that there, it's not needed, it's redundant. Aluminum can only have 1 charge. So we leave that out. If you put that in your name, then it's wrong, according to the rules. Let's see, they're going to give us another example. Yeah, examples. Okay, so potassium and chlorine make potassium chloride because potassium has a 1 plus charge always. And chlorine has a 1 minus charge, so we only need 1 of each. And we name it potassium chloride. Magnesium is an alkaline earth, which has a 2 plus charge always. So we don't need to say what the charge is. And bromine, in its ionic form, has a 1 minus charge, so we need 2 bromines to balance the 2 plus on the magnesium. Okay, calcium is an alkaline earth with a 2 plus charge. Oxygen is a chalcogen with a 2 minus charge. We only need 1 of each. All right. All right. What's the name of the compound SRBr2? Well, first thing we have to do is decide what type is it. Well, strontium is an alkaline earth, which means it has a 2 plus charge. Bromine is a halogen with a 1 minus charge, and strontium can only be that charge. It's an alkaline earth. So we say just strontium bromide. There you go. All right. Now we go to the type 2s. The type 2s are those compounds where the metal can have 2 or more different charges. It can form different ions. They're using iron as an example here. Iron cannot, and if you look at your periodic table that I've given you, there are numbers in the upper right-hand corner of each of the squares with its element. Now, some of them have what look like multiple charges, but if they're associated with anything, if it looks like there's a charge, say chlorine. Let's just take that example. If I get my periodic table and look at chlorine, let's see. Here we go. Copy of my periodic table. If I look at chlorine, it looks like a -1, a +1, +3, +5, and +7. Okay, the only one that pertains to this nomenclature is the first one. Right? Those other charges are not charges. They're oxidation states, and we haven't got there yet. We'll talk about that later. So just stick to these rules. We know which ones have a fixed charge. So if you see any other numbers in there, take the first one. That's the charge. Let's see. The alkali metals are good. They're all single numbers. Alkaline earths, they're all single numbers. Boron, aluminum, gallium, indium, they're all single numbers. That's good. Fluorine's a single number, -1. Chlorine, bromine, iodine, they have different numbers, so you have to stick to the very top one, -1 only. Same thing for oxygen and nitrogen. The top one is the one that we're interested in for this naming convention. Now, the rest of them, those other metals that can have fixed charges, that is, other than silver, cadmium, and zinc, they will have multiple values, and any one of those can be a charge. So iron is either a +2 or a +3. We could have iron like that or iron like that. It just depends on the compound. And the ratios of these elements to one another in a compound were determined experimentally before we developed this concept of charges. We'd say, okay, go to the bench, take this compound we know is pure. We've purified it. We can't break it down any further by physical means. And then we decide what's the mass ratio of this element to the other element. And then we figure out the formula. And then we try to reason, how can it be that way? Well, we knew that metals and nonmetals were positive, negative, cation, anion. So we have to assign a charge to the metal and a charge to the nonmetal. Usually the nonmetals are fixed charge. So you work from that end to say, all right, if you have this ratio of nonmetals at that charge, then the metal at its ratio must be this charge. In case of iron, it's either +2 or +3. Okay, that's the history. We've developed now the practical application of what we've learned is that we can put these metals together with nonmetals in compounds, and we still simply balance the charge. But we have to know what the charge is on the metal. Since it's variable, you have to be given that charge. Right? And we do that with a Roman numeral. If we write the name, then we put the Roman numeral in there, charge for the metal. We would do this one, we would have a 2, and this one we'd have a 3 in the name. All right, so here's some examples. Right. I think it's easier to deal with your periodic table. Makes more sense to me. I will point out one odd one. The one at the bottom, mercury. Mercury, when it's in a compound, always occurs as a 2+ charge. Now, if there's only one mercury atom in that compound, it's just the 2+ is assigned to that atom, that ion. But if it's a 2+ charge and there are 2 of them, then each of the mercuries has a 1+ charge. Okay? That's the only squirrely one that we're going to encounter, is the way mercury behaves like that. It pairs up when it's in a compound. If it needs only one plus for that mercury, then it pairs up as a 2+ binary ion. This one, of course, is going to be like that when we name it. All right. So let's take this example for iron. If we have iron and we're specifying its charge as 3+, and we're combining with oxygen, we know oxygen is 2- because It's a chalcogen. All right. So we just need to balance that charge. Well, how do you balance an odd with an even? Right? We borrow from math. Cross multiply. Bring the 2 over here and the 3 over there. And then check yourself. 2 times 3 plus is 6 plus. 3 times 2 minus is 6 minus. So that's 0. We're balanced. We just need 2 iron atoms and 3 oxygen atoms in this formula. All right. And when we name it similar to this with just that one change. We have iron oxide, and then we say the iron has a 3 plus charge. That's it. That's the name that's unambiguous for this compound and non-redundant. We have to say what the charge is because iron can assume multiple charges. Okay, if we were to say copper 1 bromide, then we know that the copper has a 1 plus charge. Bromine is a halogen with a -1 charge. So that's all we have to do. Just write CuBr. Now, I hope it's becoming clear to anyone that's viewing this video that I wasn't kidding when I said you need to memorize those symbols. If you haven't completed that process yet, you need to get on it in a hurry because the train's has already left the station and it's not going to stop. It's getting faster. So you need to know what those symbols mean and be able to go back and forth between the element name and the symbol in order to write these compounds. The alphabet of chemistry is the element symbols. Now we're making words with those symbols. That's the compound. Next, we're going to go and make sentences. Those are chemical reactions and we'll get there. Okay, if we want to say we want to name this compound, FeS, right? We know it's going to be iron sulfide of some kind. And notice on this side of the Atlantic Ocean, the sound F in this word is made with an F. If you're on the other side, say England, it's going to be PH. So if you do that extra credit naming compounds and you write, say we gave this as an example, say FeS, name it. So the answer would be iron 2, because this is 2 minus, that would be 2 plus. Right? If you write this, I know you cheated. You just went online, looked it up, and most often what you're going to find is the English version, not the American version. So I'll count that one wrong. That's why I want you to learn to name compounds and do the extra credit as practice, right? You get credit for doing practice. But if you just go online and look them up, that's cheating, and it's not going to do you a bit of good. All right. Here's another one. Let's see. I got to make some room here. Let's take that one out. If we want to name PbO2, we know that Pb is lead and oxide. Now we just have to deduce what is the charge on the lead. Well, with 2 minus here, we have a total of 4 minus. So this one lead, that formula is given to you. So the lead must be a 4 plus. That's the proper name. And we could go back the other direction because the name is unambiguous. How about this one, CrO2? Let's see, let's make some room here. If we want to name this one, we know it's going to be Cr for chromium. Leave a space because it's not one of the fixed charges. So we know we're going to need a Roman numeral, oxide. So we deduce this is a 2 minus, right? So that's a 4 minus total. Chromium must be a 4 plus. All right. All right, let's see. We're going to get a little more complicated here. What's the correct name of the compound that results from the most stable ion of sulfur? Right. So we have sulfur. Which one is that? Is that going to be the metal or the non-metal? You find it on the periodic table. It's a non-metal. And it's in the chalcogen group, which means a 2 minus charge. Okay. Between the ion for sulfur and the metal ion that contains 24 electrons. So there's some metal here that has 24 electrons. Now, we have to assume that there's only one metal here, one metal ion. It doesn't say 2 or 3 metal ions, just one metal ion. So if it has 24 electrons, and to balance this one, it needs to be a 2 plus, correct? So how did it get to be a 2 plus? It lost 2 electrons, which means it has to be 26 atomic number. So we go to the periodic table and we look, 26 is Fe. So this is Fe with a 2 plus. Our compound then would be FeS. Oh, excuse me, I want to name it. So that would be iron 2 sulfide. There it is. It helps to go back and look at the question every now and then. All right. Type 3 compounds. Let's see. Let's move this out of the way here. Type 3 compounds are made from, excuse me, 2 nonmetals. Now, we can't use the balanced charge technique in nonmetals because there are no charges. They can't form charges because there's no tendency for a metal, since there's no metal there, to give up. One does not give up electrons to the other. They have to share. So we're going to borrow from the convention that we've established so far. All right. The first element in the formula is named first as if it were a metal. So we just say the element. The second one assumes the position of the anion, even though it's not an anion. It assumes the position, so we change the ending to IDE. And since there are no charges to balance, we actually, in the name, must say how many of each atom is in the compound. And that's where the prefixes come in. The Greek prefixes, we're only going to use 1 through 10. Let's see. Yeah, on the next page. So, Greek prefixes: mono, di, tri, tetra, penta, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. Okay. Your textbook left those 2 out. What we let's use some examples. Let's do it that way. So here we have what many claim is the problem with Earth's global temperatures, carbon dioxide. It's not, but a lot of people believe it, probably because there's money in it. So CO2, we notice that this is a nonmetal and that's a nonmetal. So we instantly have to go to the convention for type 3 compounds. The first one assumes the metal position, so we just say carbon. And in that position, we never say mono. It's just convention. We don't say mono here, even though there's only one. We just say carbon. And then we say oxide here, but now we have to say that there are two of them. Dioxide. That's the name. Let's see, another example. SF4, 6. Yeah, SF6. This is sulfur. And then we say hexa for 6. Like that. Sulfur hexafluoride. And we can go this way, or we can go that way. Either way, the rules still say unambiguous and non-redundant. Here we have N2O4, right? We know it's going to be nitrogen in the first position, and then oxide, but this one says 4. Notice we dropped the A off of it. Just by convention, two vowels run into each other, we drop the one on the prefix. So it's tetroxide, not tetraoxide. Tetroxide. And this is dinitrogen, because there are two of them. Okay. All right, we're still going from compound to name. So if we do this one, let's see, let's make some room here. We got to say, all right, what's Se? Se is selenium. But is it really a type 3 compound? We know oxygen's a nonmetal. Is selenium? Yeah, it's in the same group as oxygen. And it's still above the dividing line between metals and nonmetals. So this is a type 3 compound. We say selenium dioxide. Notice that selenium's first, and there's only one of them. We don't say mono. We consider that redundant. Selenium dioxide. Here's a decision chart. We didn't do any going back the other direction. Let's try that. Let's say we have, okay, let's do this one. Name that compound. The first one is phosphorus. Right? Notice in this case, either side of the Atlantic Ocean, the F sound is pH. Right? So I can't tell if you were cheating on this one. Phosphorus, diphosphorus, and then oxide, pentoxide. Notice I dropped the A off of that one. Pentoxide, diphosphorus, pentoxide. Okay, so here's a flow chart. It's a decision chart. So if you have a binary compound, is there a metal present? Right? It'd be in the first position. If there's a metal present, then we either go to a type 1 or a type 2. Then to break the tie, we say, what type of metal is it? Is it a fixed charge or possible multiple charge? And we know which ones are which. If it's a fixed charge, it's automatically a type 1 compound, and we know how to name that one. If it's a multiple charge, then we have to say what is the charge on the metal. And we have to deduce that from the formula. And if it's not either one of those, then we go straight to this one and use the type 3 naming convention. Now for polyatomic ions. Polyatomic ions are groups of atoms that behave as a single unit ion. And I gave you a list of them. I think it's in the review document. Yeah. Next to the last page in the review document, you have a list of polyatomic ions. Now, it looks like there's a lot of them, but the one on the list on the left, name and formulas, are the same as the ones on the right. Only on the left, they're sorted by name, alphabetical name. And on the right, they're sorted to alphabetical formula. All right, so you can look on either side depending on what you're trying to find. And you will have this available to you. Any exam you have will be available, just like the periodic table. So you don't have to memorize them. You just have to know how to use them and how to name them. All right. These names, it says they must be memorized. If you do enough practices, right, you'll start to memorize them anyhow. Here's some examples. And in that table of polyatomic ions, they are all anions, negative ions, except for one. That's the first one on this list, ammonium. Ammonium is the only positive ion in there. There's one, I don't see it. Occasionally we'll get compounds with that, but that's not a polyatomic, that's why it's not here. But it does happen. All right. So it's important to remember that these polyatomic ions behave as a single unit, and they have a charge assigned to them. So where does the charge belong? Say ammonium, NH4. Where does that charge belong? Does it belong on the nitrogen or one of the hydrogens? None of them. That charge is assigned to the entire unit. It's spread over this group. Right? We have a three-dimensional structure. It's spread over the entire group is a +1 charge. Okay, so it's relatively diffuse, but it's not assigned to any one atom. That means if you need in your formula more than one polyatomic ion, you have to use a parentheses and a subscript, because the polyatomic ions are fixed formulas. You cannot change the subscripts in a polyatomic ion. Say if I needed two of these, you can't write N2H8. That doesn't work. You have to say parentheses and 2. All right. So let me erase this mess for now. So the logical question is, if you have a compound with an ammonium ion in it, that positive, where would it fit in this scheme? It would always fit right here because it's a fixed charge. These polyatomic ions have a charge, and you can't change the charge. It's only one charge. So anything with ammonium in it is a type 1 compound. So for instance, if we wanted to say, instead of aluminum chloride, we said ammonium chloride, it would be NH4Cl. We balance the charges again. 1 plus and a 1 minus. If we had, say, what would this be called? Well, let's use another polyatomic. Let's take a negative one. We've still got ammonium, right? So it's a type 1. But let's pick, say, the sulfate, SO4 2 minus. And we said we want to write the formula for this one. Ammonium sulfate. Notice we don't have any Roman numerals in here because ammonium is fixed charge. So we would say NH4, which has a +1. Sulfate from your table is a 2 minus. So we need 2 of them. NH4 taken twice, SO4, and that's our ammonium sulfate. All right. Now, there's some of these that form a logical sequence. We call them a homologous sequence. And it makes it easier to memorize them if you ever have to. Let me see, I'm going to have to make some room here. Let's make room here. Like this. All right. I picked the chlorine-oxygen combinations to illustrate. So I always start with the one that ends with ATE. ClO3 minus is the chlorate polyatomic ion. Okay? If we take away 1 oxygen, the charge is still a negative, 1 minus. ClO, let's see, I'm going to go in the wrong direction. Hold on a second. I'm going to go this direction. ClO2 minus. Right, take away 1. This is the chlorite polyatomic ion. Take away 1 more, we don't have any more suffixes that will satisfy the conditions. So we go to add a prefix. We say underneath this one is ClO minus. Instead of chlor or something, it's hypochlorite. You know, like a hypodermic needle underneath the skin. This is underneath the chloride by 1 loss of oxygen. If we add an oxygen, then we have to put a different prefix. We use per chlorate. That is above or in addition, perchlorate. And there's your sequence, right? Perchlorate, chlorate, chloride, hypochlorite. Now you can also do this with any of the halogens, right? If you have, instead of chlorine here, you have iodine. Then this would be hypo. Need to erase this part. This would be per iodate. This would be iodate. And this would be iodite. And this would be hypoiodite. Okay? And you can do the same thing with bromine, right? Perbromate, bromate, bromide, hypobromate. So there, with that convention, you've got 12 polyatomic ions memorized, just like that. There are others that do similar things like the sulfates, right? Sulfite, sulfate, nitrate, nitrite. Let's see if I see any others. There's another one in here that gives students troubles. Let's look at that one. The one where we start with phosphate. PO4 3 minus is phosphate. And these names are fixed. When this is in a compound, we say something phosphate. Like we did, it would be, if we had ammonium, it would be ammonium phosphate. And these are fixed charges. If we add a hydrogen, then the hydrogen comes in as if it were a positive charge, which reduces the negative, actually increases from a -3 to a -2. And this is hydrogen phosphate. Let's get this out of the way. Okay, add another hydrogen. The charge then increases to a minus, only a -1. This is dihydrogen phosphate. And then that's as far as the polyatomic go. If we go all the way up to 3, then it's a neutral compound, and it will be trihydrogen phosphate. Or if you dissolve it in water, then we have to use another naming convention for acids, and we're going to get there in just a minute. Hydroxide is another commonly used one, OH minus. Cyanide, CN minus. So we have a host of different polyatomic ions that behave as single units, and the names are fixed. Okay, it's probably too small to read, but that's a representation, a picture of the one that's included in your review document. All right, so C2H3O2 minus is acetate. That's the acetate ion. So if we put one positive ammonium with one negative acetate, we only need one of each. So NH4C2H3O2 is the correct formula. And we would name it ammonium acetate, the type 1 convention. Here are other examples. Sodium hydroxide, right? That's lye, the stuff you pour down your drain to unclog your trap. Sodium hydroxide. It's a very strong base, and we'll get to that again also. This one, what naming convention do we have? Look at the metal. The metal is magnesium. It is an alkaline earth, which is a +2 charge always. That's a type 1 convention. So we just say magnesium, and then what is the polyatomic? Nitrate. It's unambiguous, non-redundant. We know we have to have 2 nitrates because magnesium is a 2+, nitrate is a 1-, so we need 2 of them to balance the charge. Ammonium sulfate, we did that one already. Now, this one is a type 2 compound with a polyatomic, because the polyatomic is the negative, the cation, the anion, and the cation is a multiple charge species. Iron can be 2 or 3. So we look at the formula, right? We see Fe PO4, right? This one is always 3-. That means if we only have one of these, it has to be a 3+. No other option. So we say what it is, iron 3 phosphate. There's your decision chart, similar to the one we saw earlier. All right. What's the name of this one? Let's see. Make some room over here. So we want to name KClO3. KClO3. That brings up another indicator as to whether, when you're doing the name the compound extra credit, I've seen this over and over again. And I can tell that the student cheated on this one because they misread that representation. They thought it was CiO3. So they would write it like this, KClI. O3, and it would be wrong. So let's name this one potassium. It is a type 1. This is a fixed charge, +1. This is a -1. But what is ClO3? We just did it a minute ago. Potassium chlorate. Okay? How about this one? Examine the following table of formulas and names. Which of the compounds are named correctly? All right, so we're going to have, we're going to look at each one of these in sequence. All right, first one, P2O5. We did that one earlier, actually. P2O5. What type of compound? How would we name it? Is it a 1, 2, or 3? Non-metal, non-metal is a type 3. So we have to say diphosphorus. Let's see. Actually, you can tell. I can tell whether you cheated on this one because on this side of the Atlantic, it's RUS. On the other side of the Atlantic, it's ROUS. Diphosphorus pentoxide. Okay. That's named correctly. ClO2. ClO2. And there's no charge, right? So we're not talking about a polyatomic ion here. We're talking about a binary compound, which is a type 3, 2 nonmetals. So we say chlorine. We don't say mono, just chlorine dioxide. Okay. That one's wrong, right? This is 1, this is 2, and that one is wrong. PBI4. This one's named correctly, that one's not. Excuse me, PBI4. This is either a type 1 or a 2 because it's a metal in the first position, but lead can have multiple charges. So it's a type 2. We have to deduce. That's a -1. This would be a -4. We have to balance that with a +4. So this would be lead 4 iodide. Okay, and that one's wrong also. How about Roman numeral 4? CuSO4. CuSO4. Copper is also type 2, multiple charge. So this is a 2- polyatomic ion, and you can look it up in your chart. And this one would have to be a 2+. So we'd say copper 2 sulfate. Okay. There's only one that's written correctly. The first one. Right? The rest of them are wrong. Okay. Let's see. There was something I was going to add to this. Oh, if you're asked the question, and you're given elements in a compound, and they're both nonmetals, right? But you're not told what the formula is. Which one comes first, right? How do you tell? If it's not given to you, how do you tell which one assumes the metal position and which one assumes the non-metal position for naming convention? If we have say this one and that one, right? These two non-metals, then we see, all right, what are they? What are their symbols? And where are they located in the periodic table? The one that's to the left and or below comes first. In other words, the one that moves closer to the metal side is the first one. So, for example, if we want carbon and oxygen in the compound, then we would look and see where they are on the periodic table. Carbon's to the left of oxygen, so carbon would come first, right? And then oxygen. And then we would have to decide from the rest of the problem, what are the subscripts? If it says you have one oxygen and one carbon, then that would be the correct formula. You would not write it this way. That would be wrong. Okay, that's how you break the tie. That's how you decide which one comes first. The one that's closer to the metals is in the metal position. Now we have a naming convention for acids. All right, let's make some room. Acid naming convention. First condition for naming acids, you have to have a compound with a dissociable hydrogen, right? Or an ionizable hydrogen. The hydrogen, in that case, H always comes first. So you need a hydrogen. You need a hydrogen to ionize. HCl, right? That hydrogen. And the other condition is it has to be in aqueous solution. You got to put it in water. If we name this hydrogen chloride would be this, HCl. It's a gas. If we bubble that gas through water, it dissolves in the water. Now we name it hydrochloric acid. Okay, that's the difference. You have to have the hydrogen first. Now you can have other hydrogens in the molecule, but only the ones that are at the beginning of the molecule are the ones that make the acid. The other hydrogens are locked in place. They cannot move. All right. So the rules. You look at the formula and you look for oxygen. Is there oxygen in the formula? Right? In this case, no. There's no oxygen. So the name is preceded by hydro. If there are oxygens in the molecule, for instance, like this one, HNO3, aqueous. If there is an oxygen there, you don't say hydro. Okay, I'll tell you what you do in just a minute. In this case, you say hydro, and then you change the ending here to ic. Ide becomes ic acid. All right? Hydrochloric, even a polyatomic that has no oxygen in it, Cyanide. Hydrogen cyanide in aqueous solution becomes hydrocyanic, I to ic, hydrocyanic acid. Sulfur, it would be, let's see, hydrogen sulfide is the correct name for that. But if we put it in water, now it's hydrosulfuric acid. Okay, here are a number of examples. All of the halogens that are bound to one hydrogen are hydros. Hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And then you have the polyatomics possible. And most of the polyatomics have oxygen in them. So they would come under the second rule. If the anion contains oxygen, excuse me, then we look at the polyatomic that forms that. This is a nitrate. Eights become X. So we say nitric acid. Okay? No hydro. Nitric acid. SO4 with an H2. Now, why is it H2? SO4. Because this polyatomic is a 2 minus, and hydrogens are a +1. So we balance the charge again, and in this case, actually they're not really charged, but that's a little too deep for us here. But the concept is the same. We have H2SO4, and since there's oxygen, we don't say hydro, we just go to this polyatomic ion, this sulfate. 8 becomes ic. So it's sulfuric. We don't say sulfic, it just doesn't sound right. So sulfuric is correct. Here we have the acetate ion. Acetate has one hydrogen. It also has oxygen, so we don't say hydro. We just look at the acetate. 8 becomes ic, acetic acid. Acetic acid. 5% acetic acid is vinegar. All right. Now, if it's 8, it becomes ic. If the polyatomic is ite, like this one, HNO2, well, without the aqueous, this would be hydrogen nitrite. And the ite, in this case, becomes us. So it would be nitrous acid. Right? The ite becomes OUS. So there's your nitrous acid. SO3 is sulfite, not sulfate, it's sulfite, so it'd be sulfurous acid. ClO2, we named it before, was chlorite. Ite becomes us. Now, what about, let's go back to that homologous series. What if it's this? Perchlorate. 8 becomes ic. So it would be perchloric acid. Right? And that would be HClO4 aqueous. Okay? We keep the prefix because that's part of the polyatomic name. We just change the ending from A to ic when we call it an acid. Perchloric acid is extremely hazardous. It's a very strong oxidizing agent. If you put it in contact with concentrated organic matter and you don't let it slowly react, if you heat it up, then it'll explode. Right? Oh, you could take a beaker of perchloric acid, concentrated perchloric acid, and drop a nice big chunk of butter in it and put it on the hot plate in your fume hood, turn it on high, pull the sash down, and evacuate the building because it's going to blow that lab out. All right. So here's your decision chart. Does the anion contain oxygen? No, start with hydro and just change the ending to ic, right? Like hydrochloric acid. If it does have an oxygen, then you check the ending to see if it's an ate or an ite, right? And it just depends on the sequence, right? If the polyatomic has an ATE ending, you make the acid an ic. If it's an ITE ending, you make the acid an us. All right, which one of these is named incorrectly? Okay, we're going backwards now. Let's see, I think I've got time to do this. So let's make some more room. All right, let's see if this one's named correctly. A, B, C, D, E. A, B, C, D, and E. First one, KNO3. Let me put them all up here first. TiO2, SNOH2, 4, excuse me, 4. 4. And PBr5. Okay, and H2SO3. H2SO3. Okay, I see an acid in there. Let's be accurate. It should be that. Okay. All right, now let's name them. Type 1, 2, or 3. Type 1, potassium is a fixed charge. It's an alkali metal. So we just say potassium nitrate. Okay. 1, 2, or 3. Type 2. It's a metal, but titanium has multiple charges. So we have to figure it out. This is a 2 minus. That makes a 4 minus. This has to be a 4 plus. So we say titanium 4 oxide. Right? That one's wrong. SNOH4. Well, this has, find out where 10 is. 10 is a metal, and it has multiple possible charges. So if this is a -1 and we have 4 of them, this has to be a 4 plus. So we say 10, 4 hydroxide. Okay, that one's correct. This one is a non-metal, type 3 compound. So we don't say mono because there's only one of them. We say phosphorus, penta, bromide. Phosphorus pentabromide. Yes, that's correct. This one is sulfite. Aqueous solution. It's an acid. Has an oxygen, so we don't say hydro. We just take the I and make an us out of it. So we say sulfurous acid. Okay, that one's correct. So there's the only bad one. Now, how about writing formulas from names? The first one is sodium hydroxide. Sodium, all right. Is that going to be a type 1 or a type 2? Because it's a metal, right, is a type 1. Sodium is a fixed charge. Hydroxide is a polyatomic ion. So we have sodium with a +1 charge, hydroxide with a 1- charge. That's it. That's the formula. How about this one? Potassium carbonate. Well, we know we're going to have potassium with a fixed charge. Carbonate is a polyatomic ion. You know, look it up in your chart. CO3, 2-. So that means we need 2 of these positives to balance that carbonate. There you go, potassium carbonate. Sulfuric acid. Okay, working backwards. Sulfuric acid. Okay. Does it have oxygen in it? Yes, it does, because there's no hydro. Right? There's no hydro here, so we have to say, where did that ick come from? It came from ATE. That means sulfate. Oops. Try that again. That means sulfate, right? And if it's an acid, it has hydrogen. Sulfate is a 2- charge, so we need 2 hydrogens. 2 hydrogens. And sulfate is that. And it's an acid. So that's the formula for sulfuric acid. We left out the aqueous. That's an oversight. How about dinitrogen pentoxide? We can tell that this is a type 3 because of the prefixes. Dinitrogen pentoxide. Like that. That's all there is to that one. Those are the easy ones. The nonmetals are easy because we tell you exactly how many atoms go into the formula. Cobalt-3 nitrate. All right. The clue here is the Roman numeral. Cobalt has a 3+ charge. And nitrate is a polyatomic ion. And look it up, it's a 1- charge. So we need 3 minuses to balance that cobalt. Okay? All right. Okay, we're going to do some Sherlock Holmes here. A compound has a formula XCl3. Okay? We obviously don't know what the X is yet. X could represent a metal or a nonmetal. All right? What could the name of this compound be? Well, if it's a metal, excuse me. If it's a metal, then we've got 3 minuses here. That means this is a 3+. That doesn't tell us much, does it? X represents a metal or a nonmetal. Oh, does it give us choices? It gives us choices. Okay, so this is a multiple choice, and we can say, all right, if that's an X3, we need a metal with a 3+ charge. All right, start from the bottom. Magnesium, nope, 2+ charge. Tin, 4+ charge. So it's not the metal. Can't be the metal. Doesn't fit. So how about phosphorus trichloride? Yeah, that works. Carbon monochloride. Well, I've never heard of that one, but it wouldn't fit because mono is only 1 and we need 3. So A is the only one that works, right? It's a multiple choice problem. We eliminated the ones that didn't work. That's Sherlock Holmes. Eliminate the ones that are impossible, and what's left, no matter how improbable, must be the correct one. That came out of one of Conan Doyle's books. I don't remember which one. But it was spoken by his character, Sherlock Holmes. Okay. This is our last slide, I believe. And this is not included in your textbook. I don't believe it is. But you will encounter it. this naming convention. This is the way to name compounds that have waters of hydration. What we mean is there's a compound here, and it's always metal, nonmetal. It's a 1 or a 2. And there are waters associated with it. In the crystal structure of the solid are waters. They're separate water molecules. They're just placed in positions throughout the crystal. And they're in a regular, actually they're molar ratio with the compound. For instance, let's see, let me pick an example. How about this one? Zinc chloride with a 2. And then we have so many waters attached to it. Notice that this period is in the middle of the line, not at the bottom. It's not really a period. It's a connecting dot. And this tells you how many water molecules are associated with each one of these formula units. Okay, that's the way you write it. Water is part of the structure. So when you name it, zinc sulfate's a better one. Let's use the one example there, zinc sulfate. This is a 2 plus and this is a 2 minus. So zinc sulfate's a better example. So you write the compound, zinc sulfate, as this. And then you add the waters as instructed with Greek prefixes. How many waters are there? Well, in this case, X is 7. So we would say zinc sulfate. Let's see, zinc. Yeah, zinc is a fixed charge. So we don't need Roman numerals. Zinc sulfate, and then heptahydrate. There's the water. There's the number of them, right? And there's the compound. That's how you write the name for this compound. Another one that my general chemistry students use in one of their experiments is copper 2 sulfate, but it's also 5 waters. So this one has multiple possible charges. This would be a copper 2 sulfate pentahydrate. Okay? And we're still unambiguous. This means that and only that, and it's non-redundant. All right? So if you ever see a compound written like that, you know that these are waters of hydration. Now you can remove those waters, right? If we take, if we isolate, say, zinc sulfate from solution, right? We get it to precipitate out as a solid in aqueous solution, and then we filter it, right, to remove the zinc sulfate, and then we dry it. Right? We put it in an oven at 105 degrees Celsius. That's supposed to drive off water because water boils at 100 degrees. But we have water left behind. How do we know that? We weigh it before, right? Actually, after we dry it, we weigh it, and then we stick it back in the oven and increase the temperature to 150, 175 degrees, and then we weigh it again, and its mass is decreased because we didn't get all the water the first time. What we left behind were these waters right here. So the waters of hydration need extra energy to get loose from the crystal. And then we have what we call anhydrous zinc sulfate. Okay, that's the last one, I believe. Yep, that's it. Stop the share. Oh, What happened to Amer's gone? Okay, well, I'll stick around for a minute or two in case he comes back. Otherwise, um, this video is done. Now, what we're going to do is we'll have a review next Tuesday. I believe that's the way it goes. Next Tuesday, actually, Tuesday, next Tuesday is a buffer day. This is the 5th. Let's see, 6, 7, 8, 9, 10. Yeah, next Tuesday I put that buffer day in there in case we ran long. But since we're finished, then I'm going to uh, zoom in on that day and use it as a tutorial session. In fact, I'm going to start the reviews on that buffer day and finish the reviews on Thursday. That way we're not rushed. I can move through half of the review document, the ones that I have marked off, and anyone that shows up in the Zoom session can ask questions and we can resolve problems. And then the following Thursday, we'll finish the review. Yes. And then Tuesday the 17th, that would be a week from next Tuesday, we'll have the exam 2 on chapters 4 and 5. That gives you enough time to finish memorizing your symbols, learn these rules for naming compounds, and practice, 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 practice. If you don't practice, it will be obvious on your exam. You will fall flat on your face if you don't practice these naming conventions. And that'll only spell disaster for a future because you have to know how to name them in order to name these words, chemical formulas and names, in order to go to the next step and write chemical reactions. If you can't do that, then you're in deep trouble. I'll just be honest with you. Okay, well, that's it. Since I'm here by myself, I'm going to call it quits for today.